Okay, so there's yet more kind of fairly new concepts flying in, which are going to become of use when we talk more about co-products. So remember this idea of delta A being the classifying arrow of this diagonal arrow, 1A, 1A. So this, of course, has the property that delta A after H, K sends everything to true if and only if H equals K for any pair of arrows H and K from some objects capital H to A. So you can see all this math on the screen now, although it's kind of thing I've gone through several times. So yeah. Okay, so we define the singleton arrow, which we call curly bracket subscript A, to be the transpose of delta A. Now, the way I like to think of this is, okay, I like to think of it in terms of sets often, and then a sort of arrow into omega to the power of A. If we're working in the category of sets, well, the elements, we have this kind of thing, like in general, let's say we have an arrow from B to omega to the power of A. Well, we're going to have some arrow from B times A to omega, and then essentially this is really going to correspond to a kind of sub-object R of B times A, and then this is going to be the classifying arrow of it, and this is going to be the transpose of it. So basically, what you can think of this as doing is it's sending every element of B to the set of stuff in A, which is in this R relation to it. Now, in this kind of case, our relation is this diagonal relation here. So basically, you can think of this as sending every element A to the set of stuff in A which is equal to that element. I mean, if this was happening in the category of sets, but of course it's not really sending it to a set of stuff, it's sending it to a kind of element of omega to the power of A, which is corresponding to a kind of subset. So essentially, all you can think of this as doing is kind of converting from an element of A to a kind of singleton set in omega to the power of A, although it's doing the kind of topos generalization of this kind of concept. Anyway, it's more clear to understand it more precisely. So let's just consider a general arrow from some general object H into A. We'll call it X. Now, when we do curly bracket subscript A after X, we have shorthand for that. We call that X in curly brackets. So this is very important then. Remember, when we do evaluation, so this is like this kind of stuff, going from something in omega to the power of A times A, well, we can think of something like that as like a sub-object, and this is like an arrow, and then E is sort of testing if that arrow is in that sub-object, okay? So when we write, so we suppose we have, for a general object H, we have arrows little x and little y from capital H to A. Well, then we claim that this is true. The evaluation after y in curly brackets, comma x, is sending everything to true if and only if x equals y. So basically what this is saying is sort of that x is going to be in the kind of sub-object corresponding to this precisely when we have that these two arrows, x and y, are equal. So it's helpful to think about this in the case of a category of sets when capital H equals 1, but this is obviously much more general. So let's see the proof of it. So the proof's pretty straightforward. Remember, we're defining this curly brackets A thing here as being the transpose of delta A. So then E after curly brackets A times identity A is delta A. And so this triangle commutes here. Also, this triangle commutes here just by looking, you know, what's curly brackets A times 1A after this? Well, it's clearly this. So this whole diagram commutes, and so we then have immediately we have x equals y if and only if delta A of y comma x sends everything to true, as in this arrow sends everything to true, and that's equal to this arrow here. So this happens if and only if e after y in curly brackets comma x sends everything to true, and that's what we wanted to prove. We also get another interesting result. And so suppose we have arrows y and y dash from h to a. Well then, okay, we really want to show that curly bracket subscript a is a monomorphism. Okay, so suppose we've got two parallel arrows coming into a, y and y dash, and let's now suppose that doing curly bracket subscript a on y gives the same result as doing curly bracket subscript a on y dash. So in other words, we're supposing that y in curly brackets equals y dash in curly brackets. Well then, doing the evaluation arrow on y in curly brackets comma y, well, that's going to send everything to true because the thing in the curly brackets is equal to the other thing, and therefore these two things inside are equal. So, well, of course we have y equals y. So yes, sorry, I should say because these two things inside are equal, this does indeed send everything to true. But also, because we're assuming that y in curly brackets is equal to y dash in curly brackets, this must be equal to e after y dash in curly brackets comma y. And so that must also send everything to true. So we must have that y dash equals y. So we started by supposing that doing curly bracket subscript a after y equals doing curly bracket subscript a after y dash, and we ended up with y dash equals y. And that shows that curly bracket subscript a is indeed a monomorphism. So you can kind of think of it as this sort of thing that sends stuff in A to these kind of singleton sub-objects. Although it's an interesting kind of study topic to sort of visualize how this kind of thing actually works in particular categories, such as the category of functions and so on.